Advent of Code 2019, Day 9. And it is called Sensor Boost. You've just said goodbye to the rebooted rover and left Mars when you receive a faint distress signal coming from the asteroid belt. It must be the Ceres monitoring station. In order to lock onto the signal, you'll need to boost your sensors. The elves send up the latest boost program. Basic operation of system test. While boost, your puzzle input, is capable of boosting your sensors, for tenuous safety reasons, it refuses to do so until the computer it runs on passes some checks to demonstrate it is a complete ENCODE computer. Your existing ENCODE computer is missing one key feature. It needs support for parameters in relative mode. Parameters in mode 2, relative mode, behave very similarly to parameters in position mode. The parameter is interpreted as a position. Like position mode, parameters in relative mode can be read from or written to. The important difference is that relative mode parameters don't count from address 0. Instead, they count from a value called the relative base. The relative base starts at 0. Okay. The address a relative mode parameter refers to is itself plus the current relative base. Okay, so maybe the relative base is just another register that's part of the ENCODE computer. When the relative base is 0, relative mode parameters and position mode parameters with the same value refer to the same address, right? Because you're not adding anything to the relative base, adding anything to the parameter. That makes sense. Given a relative base of 50, relative mode parameter of -7 refers to memory address 50 plus -7 equals 43. The relative base is modified with a relative base offset instruction, opcode 9. Adjust the relative base by the value of its only parameter. The relative base increases or decreases if the value is negative by the value of the parameter. Okay, so we just need to extend the addressing modes to add this relative base. If the relative base is 2000, after instruction 10919, the relative base would be 2019, because this is the 09 is the opcode for adjusting relative base. 1 means immediate mode, and 19 is the immediate value, so we're adding 2019. 204 -34 means we're going to read instruction 4 is the output instruction. I'm guessing. I don't remember. I'm just reading from here. 2 means use the relative base, which is 2019 -34, and we get 1985 as the output. All right, so we can extend our ENCODE computer to do this, and then we can add, looks like we have some example programs here. The computer's available memory should be much larger than the initial program. Memory beyond the initial program starts with the value 0 and can be read or written to like any other memory. That's fine. I think we can handle that. It is invalid to try to access memory at a negative address, though. Okay. And the computer should have support for large numbers. I think we already do because we're using i64. We can always extend it to i128 if we need to. This one looks like a very large number, but we'll find out. Hopefully that's within the i64 range. The boost program will ask for a single input. Run it in test mode by providing it the value 1. It will perform a series of checks on each opcode, output any opcodes and the associated parameter modes that seem to be functioning incorrectly, and finally output a boost key code. Once your ENCODE computer is fully functional, the boost program should report no malfunctioning opcodes when run in test mode. It should only output a single value, the boost key code. What boost key code does it produce? All right, so before we start work on this, obviously we're going to have to make our ENCODE computer handle relative addressing mode. So let's go over to ENCODE. We're going to add a new addressing mode. And then we're going to add to the computer, I guess we can add it here, the relative base. And it's got to be an i64. I chose IP as usize because we're indexing into memory. But we're going to have to play around with that, I think. Okay, so the relative base starts out at 0, which is good because that's what the default will do for us. That does it here. Okay. And then we have to implement opcode 9. So let's add this as a test. Ooh. Oh, there we go. I did a triple click and then it reset itself. So that's good. So we're going to say test. And this is relative base Quine, because it says it takes no input and produces a copy of itself as output. So we can actually test that. Let mut computer equals int code new this. There we go. It takes no input, it produces a copy of itself as an output. So we should now be able to just loop over this as a vec. Let output equals vec bang this, and assert that as we run the computer, we have this run until output. We should loop and get all these values. Well, we can just say loop. Let next. Actually, what we could do is this. We could just, oops. For val in output, we can consume it because we're not going to need it. We're going to say let num equals computer run until output, and then we're going to assert eq val and num, and then we're going to assert that we're done, right? So we can do this, assert run until output produces a none value. What did I, oh, val in. And we're missing this, the new addressing mode. Addressing mode, relative. So we're going to take memory at, so we have the address. No, we have the value that we modify, right? So it's like an immediate mode value. So we take the value at the memory address, is that guy, and then we're going to call it the, add the relative base. And then this produces an I64, right? But this is now the new value. So now we just self memory offset. Okay. Relative is never constructed. That's true. So let's construct it. Oops, I didn't want to do that. Not down here. Oh, we got to fix the test. I just saw the error there, but we got to change this here too to self relative. Okay. And then over here, we're going to hit the test and it's going to fail because of this thing here. This should unwrap. So we should be getting these numbers. Instruction 9 is unimplemented. Perfect. So now we can implement instruction 9. And all instruction 9 is going to do is going to get the value. And we're going to modify the relative base by that. And now we know we used up 2 memory locations. Okay, so here it's trying to make a copy of itself at index 100. So this is where we have to extend our memory model so that we can write to values. And we just hit it on line 54. Does it say what values are in memory? Memory beyond the initial program starts with value 0. Okay. So I guess one thing we could do, and I don't know if this is going to make things worse, is we could make memory a hash map. And that way we don't have to have, if we're not using sections of memory, right? If we write to location 1 million, we don't have to have all 1 million numbers in between. I think instead what we want for now, let's see if we can just make it a vec. But that means what we can do is we can write a memory read function, or a memory set and a memory get function, which will extend our memory vector with zeros. And then we just modify all the places where we're reading memory or writing to memory with the set and get instructions. So fn mem set address usize value I64, and we don't return anything. We're going to say if address is greater than or equal to self memory len, then we'll say self memory. We're going to extend by vec bang 0 semicolon self memory len minus address. No, the other way around, because it's just shorter. Address minus self memory len plus 1. And then we can return, we can set the value. Self memory address equals value. And then we have mem get also. Mem get self address usize and returns a value I64. And we don't need to extend the memory, but what we can do is say if address is less than self memory len, then self memory address else 0. And now every place we index into memory, we should do that. And actually what I should do is just implement memory as a thing that takes an index and does all of this work for us. But we could just say self mem get from location, mem get. Where else do we have self memory? Right here. Mem get. Okay, mem get. And this is mem set. Right, all of these should, all right, 147. Okay, so we can just change these one at a time here. Mem set. All right, so we're obviously not using any of the other instructions, but this is all working now. And it looks like it passed the Quine. Where's the Quine? Relative, here it is, relative base Quine. Let's test the other programs. This should output a 16-digit number. Okay. How do we test that it's outputting a 16-digit number? 16-digit number. Let computer equals int code new this. Let num equals computer run until output. We can say assert EQ 16 format bang num len. Unwrap. And that test passes. I'm looking over here to see that the tests are passing. All right, and then finally, this should output the large number in the middle. Okay. Large number. So we can grab these lines here. And we can just say run until output, and we can assert that it's equal to this large number in the middle. Okay, and that test passes. All right, the boost program will ask for single input, run it in test mode by providing a value 1. All right, so what we're going to do for part 1, I obviously have to change all the other memory accesses. There's a few others. Let's see how many there are. These ones don't count because these 3 at the top are part of the memset and memget, but there's a few more. Okay. So if we flip back over, oh darn, 1909, yeah. We come over here, we can grab the input. You know what? We should commit the changes for the encode computer first. Let's do that. Status git diff git commit -m added relative mode to some of the instructions. We have to finish the rest by changing those memory things. All right. But meanwhile, what we can do is insert a new computer here. And then let lines equals AOC lib read lines. I think it's just going to be a single line. Input 2019-09.text. And then it's probably going to be self computer equals int code new lines of 0, I believe. Let's pull that in. And then we're going to say get input 2019 day 9. Yeah, it's 1 line long. We can see that here. And it's this giant computer. So we're going to see what blows up now and then slowly fix all the encode stuff. So let's run this now, and this we have to provide it a value for part 1. We provided an input value of 1. So we say self computer dot I thought I had like a push or something. Yeah, push the value of 1. That provides the input value of 1, and now we want to run until output. And we're going to print out the value that we get. If I say run until output, then the next run into output should be a none, unless we came up with a problem. So if I say let answer equals self computer run until output, if self computer run until output is sum, that means we had an error message or an error something. Then we can say panic error with answer equals answer. So this is not the key code, it's an actual error. Otherwise, we're going to say print the answer here. It should always give me something. All right. All right, let's run this. Okay, so now we have to fix our encode computer, line 105. And I don't mind fixing all of these. Oh, look at that. So it could be position or relative. So we're saying here that we're forcing whatever this instruction is. This is a input instruction, and it's got a relative addressing mode. All right, so this is interesting. We have to modify our code here to say, okay, if we have relative mode for our address, we still need to get it. So I think we should still say self read mode A. And then we have to assert that, let's say, matches mode A is either position or relative. Why is that wrong? Oh, because I did this. There, that's better. And not assert EQ, but just assert. Okay. We panicked. Oh, we panicked. So we have an incorrect answer somewhere. Probably because of one of these memory things here. So let's fix all the remaining self memories. So this is mem set. This is mem get. Like that. So this is mem set. Like that. And then what else do we have? Oh, dest. Oh, self IP plus 3. Oops. As usize, like that. We still didn't fix all of them. So this is a mem get. What else? This is poke. So this is, yeah, this is going to go directly to it. That's fine. So peak, we got memory reset, and this is mem set. These are our memory things. Yeah, we don't need to do a mem read because we're not giving it. Oh, yeah, this has to be because it's part of the program. So that we don't need to worry about that one. We don't need to worry about that one. Here's one more. So this is mem get and mem set. Okay, so it's saying error with answer 2 equals 203. Maybe 203 is the instruction that's failing. Output any opcodes that seem to be functioning incorrectly. Okay, so we must be calculating relative mode wrong then. Let's take a look at the input, 2019-09. Where's the first 203? It's right near the front here. So 3 is this here where we're trying to get, we're trying to do an input. So we can take a look. Oops. Here. So what's it trying to do? 203, 0, 1008. Oh no, 203, 0. So it's saying base relative from 0. Oh, yeah, that's right. I'm doing a self read. It should be a relative mode. And what we could do is print out as we change the addressing mode. And it should be this. Okay, so let's do that. Println new relative base equals. So we can see that. We should see that. Yep. So it's 1,000, sorry. And we should see that here. What was it? Instruction 9. There's instruction 7, instruction 5. I do see instruction 9 here. Oh, it's a relative base off of 3. Okay. That's probably what I did wrong then. No, I did that. I did the relative read. Let's see if we're doing this right. Println memory address is this. Result is offset. Self memory address. Memory 18 is 12. 26 is 0. Oh, this is the, yeah, what I need to do is flip over here and print it out before I run the next one. Println answer. Oh, and that way we'll see. Oh, interesting. It exited right away. Okay, so 26. Let's do this. Let's take a look at the input. 2019-09. 25F comma. Yeah, so it's this bit here. 2030, but this should, yeah, so this is 0 plus the relative base of 1,000. And then it's checking 8. What's instruction 8? Oops, over here. If A is equal to B. If it's equal to 1. Oh, if 1,000 is equal to 1, then we jump 63, I guess. Yeah, I wish I knew how to decode all this stuff. Let's see what we're reading and writing to different parts of memory. Maybe that's a problem here. So println writing value to address. And we can just say reading from. Then we're going to have to clean all this up, obviously. Okay. Like that. Okay, so it looks like it's checking reading 203 from 25. Yeah, so it's just that's just reading the instruction, I think. Maybe that's the problem. Yeah, this doesn't need to be a memget. We can just look in memory directly. Although it does tell us what the instructions are, or what the instructions are doing here. And then it says reading 104 from 50. Is that right? Reading 203 from 25. Yeah, so that's this instruction here. Memory 26 is 0, so the result is 1,000. Oh, yeah, and then, right, result is 1,000, and we get that. We do a memget. Then it says reading 3 from 1,000. Where did we write? Yeah, we wrote 3 to 1,000 here. And then it says writing 1 to 3. Why is it writing 1 to 3? This should be reading from 1,000 and checking to see if it's equal to 1. That's what the 1008 does. And then it writes the answer to 63. Let's print out the instructions as they come out. Instruction 9, right? That's changing the relative base. Saying instruction 104. 4 is output, right? Yeah. 4 is just saying, okay, just output it. So it read 203 from 25, and then the next instruction it executes is 104. I think something's, This was supposed to be pretty straightforward, right? I mean, just modifying all of the reads so that they handled relative mode. Instruction 1008. Okay, so we start with what? 1102. That's instruction 2. Reading 3 from 63. What is instruction 2? Instruction 2 is multiply. So we're multiplying these two values and storing it in 63. Yes, storing it in 63. So that's where we got the writing this to 63. Okay. Then we have instruction 1007. We read that from 63. What's instruction 7? Check to see if A is less than B. And it isn't. So we come to instruction 1005. 1005 is if it's not equal to 0. It is equal to 0. So then we get to 1101. Instruction 1 is addition. Yes, it's addition. So we're adding 0 and 3 and putting it in location 1000. Okay. Then we have instruction 109, which sets a new relative base to 988. Then we have instruction 209, which sets the relative base to, well, it should be set to whatever's in address 12 plus 988. And it, which should be 3, right? The result is 1000, and then we return 3. Get reading 3 from 1000, and then it says the new relative base is 991. So we added 3 correctly to 988 and got 991. And now it's saying add instruction 9 from position 1000, so it should be 3 still, and it gets 994, correct? And now 209, which means relative from 994 plus 6. Yeah, 994 and 6 is 1000, and we got 3 again. Okay, that's all correct. And now we come to instruction 209. Oh, maybe this is different 209. Maybe that's what I'm saying. Okay, here's 209. 209 means 3 plus the relative base. The relative base is currently 1000, and we're adding 0. And 3 is what instruction? Input. So we input that and we store it in 1000. So we inputted value 1. So now 1 is in 1000. Is this the bug here? All right, so we should be taking the input and writing it offset 0 from the relative base. The current relative base is 1000. And for some reason, we're writing it to the value 3. That's the bug. Instead of writing it to 1 to 1000, we're writing 1 to 3. Okay. Yeah, we're trying to read. Yeah, the result is offset. If we're trying to read, why is my brain not working here? This is the address we're trying to read from. It was working for all the other values when we were doing that. Let's take a look at the difference here between 9. Yeah, so we did a read using that mode to get the value. And now what we're doing is we're trying to set, when we're trying to set something, we don't want to read from the memory. We want to actually calculate what the value is supposed to be. But the test for input works, right? If I run the test, oops. Oh no, we have 10 failures now. Okay, yeah, let's fix this. I think I messed up the, when I modified this, I must have messed things up. So let's figure this out. First of all, we're going to get rid of all these prints. That's just killing us. Yeah, so we messed up. We messed this up. Example 1. Oh, these are the tests from day 7. Okay, let's fix this here. Copies input to output. Yeah, okay. So let's fix this. 3. So this is the bug. Somewhere here. So what did we change? Git diff. Here. I was asserting that we were in position mode, but now we can have position or relative mode. So we do need to get the address, which I thought would be in A. Oh, this is doing a self-read using this mode rather than getting the address for that mode. That's the difference. Let's call it address 4. And that way we can get the address for a particular mode. So fn address for self address usize and return to usize. And then we do something very similar to this. For position mode, we just return the address. For immediate mode, we panic. And for relative, we just return that. Right, and that gives us the address for something. And that, now we don't need to include this assert here because that'll be taken care of here. Oh, we need the addressing mode. Still not quite right, because the other problems that all the other bugs I introduced. Oh no. Okay. Okay, let's find out why this is wrong. Println address for input is equal to address. And let's look for address for input is 1. So input at location 0. It says write to 0. Why is it coming up with a 1? Oh, because we need to actually read of this. There. That's the bug. Okay, so that allows that to those tests to pass. If I hit run, we have a bug here. And it's 161. Oh, now it's assuming that this is going to be in position mode. But we need to have it also be, so this needs to be address 4. Okay. And so we're gonna end up with a bunch of these. Line 107. We're gonna have to do this for all of the desks. We don't need this anymore. Any more desks? Yeah, here's a desk. Address 4. There's probably a way to do it without being all annoying. Okay, so now we have a number. We came up with an answer. Let's switch back here so we don't print the answer too soon. Let's see if this fixed all the problems. Yay, it did. Okay, so let's clean up our encode. Get rid of all these prints. That's it. Make sure the tests still all pass. And we can commit these changes. Git status, git add source encode, git commit, fixed up relative mode addressing, hopefully. I am full of hope that I've done that. Git status, git commit -am 2019 day 9 part 1. Done. Okay, let's see what part 2 is. You now have a complete encode computer. Yay! Finally, you can lock onto the series distress signal. You just need to boost your sensors using the boost program. The program runs in sensor boost mode by providing the input instruction the value 2. Once run, it will boost the sensors automatically, but it might take a few seconds to complete the operation on slower hardware. That's bad. That's bad. Do we have to do another program analysis thing? In sensor boost mode, the program will output a single value, the coordinates of the distress signal. Run the boost program in sensor boost mode. What are the coordinates of the distress signal? Oh boy. I'm going to quit out of Bacon because we might end up in a very, very long loop. Let's just take a look at 1909. We will then do a self-computer reset. Self-computer push 2. Right, it said give it the value 2. We're going to push 2. And now we're going to just do here. And this is probably the part where it's going to fail. Self-computer run until output. Unwrap. All right, cargo run. That doesn't look right. I did a reset. Oh, you know what? I didn't do a reset. Self relative base equals 0. There we go. Now I've done a reset. Oh, okay. I mean, it's a number. That's the right answer. So what was it? I mean, it did take a little while to run in debug mode. Let's see what release says for us. Yeah, 10 times faster. I would have thought that it would be more complicated. So part 2 really didn't have anything to do. Interesting. I thought that was going to take a while.